So it's visible, right?
Yes, ma'am.
Where is pointer? So when it is a hypoeutectic alloy, if this is a cross section of alloy, we are just watching under microscope. The structure is like this. Needle-like structure is only seen in case of hypo. But when we are talking about hyper, there different type of silicon structure or primary silicon structure is also observed apart from that needle like hypostructure. So these are silicon tetrahedral structure. So as I have said, silicon can extend their bond and it can drastically form a mesh like structure all over the alloy. So these structures are made of the silicon, primary silicon, in hyper eutectoic alloy. And what happens is, when there is a, it's a tetrahedral shape, and when there is a plane which is a twin to each other. Twinning plane means if there is a plane and according to one direction there is another plane which is a similar mirror image of each other. If according to this direction there is a plane, so it will be called a retrant edge. So what happens in silicon is, due to its own characteristics, from that twin plane it will grow another silicon mesh like structure from that particular plane along that particular direction. Along this direction it will just make a stair kind of structure from one to another, from one plane to another plane, and it will look like this. From side view it will look like this. You understand? This is the front view, but this is the side view. From front, if there is twin plane, means if this is one plane and according to this direction there is another plane where these two planes are mirror image to each other. So according to that direction it will start growing some fibrous structure, and this age is called retrant age. And this grow is obvious in case of silicon. As I said, silicon creates a mesh like structure in all over the alloy. It has that capability and it's the inherent property of silicon. If it founds a twin plane it will start growing like this, and due to this type of structure it will increase the brittlity inside the material. So it's called the growth of silicon inside the alloy. And due to this growth, if there is one particular suppose this is one particular SI structure, okay, and after few times that silicon has made its growth from that retrant age, and now it's looking like this. It's much broader, it has some steps inside it according to a particular direction, and it has grown in that particular alloy. So it will certainly increase the brittlity. And if we are using aluminum alloy, we are always aiming for uh, an application where the ductility is needed for the aluminum, because aluminum is famous for its ductility. And the aluminium is famous for its ductility and its low density and its low weight, this sort of features. And we, if we are getting this type of silicon structure which introduces a lot of brittlity, it will be of no use. So this is a problem in hypereutectic alloys, but obviously there is solution for the for this type of problems. So I think you'll know about the solutions in the later on videos. There are some elements like strontium, sodium, barium, which are added in the aluminum silicon alloys, perhaps, to eliminate this type of growth. So is it okay?
Yes, ma'am.
Excuse me, ma'am.
Yes, yes.
Ma'am, actually, a doubt. This sort of fibrous growth, this similar thing is exactly happening in primary silicon as well as in the needle-like structure that we see in hypereutectic and hypereutectic, right?
No. In hypereutectic is happening
Uh,
more, because
o-
why more? Because the silicon percentage has certainly increased in case of hypereutectic. In case of
yes.
hypoeutectic, the silicon percentage is not that much. So it will be there, but it will not affect that much. But where the silicon percentage has increased more than 12%, so it will be a problematic situation for hypereutectic alloy. That's why we are more concerned about the hypereutectic alloy, because of this growth of the silicon.
But in hypoeutectic alloys also, because like the presence of that primary silicon can increase its hardness like a lot. So is this method like a good way to convert it into something which is fibrous and support in that enhances mechanical properties in that way?
uh, Mixture of what? Means we are mixing
Uh,
silica or
I mean that like this method to convert primary silicon to maybe fibrous silicon, will that help better its properties? Because I guess the presence of such primary silicon can make it brittle.
yes.
So,
So in
if
real
it
life application also, whenever we work with any aluminum alloy which has a certain percentage of silicon, even it is not a hypereutectic alloy. For hypoeutectic alloy also, sometimes we mix this type of strontium or barium or sodium, just in case to avoid the growth of the silicon inside. So there is always a kind of growth in of the primary silicon, but as the amount of primary silicon is more in case of hypereutectic, that's why we are more concerned.
yes, ma'am, but the mechanism is exactly the same, like this twin boundary
Yeah,
formation. And,
it
okay,
will
okay.
happen. Okay, it will happen. When you'll go through the next videos, you'll see how this externally added materials will just change the growth sites. It cannot stop the growth of the silicon element inside the alloy. It will just change the growth of the silicon sites or growth of the sites, so that a continuous growth will not occur, because a continuous growth like this will drastically hamper the properties. It can drastically increase the brittlity, that what we don't know, we don't want. So that's why those type of uh, materials or elements are added.
Yes, ma'am, got it. Thank you.
Okay, next.